Hello there. We're in Lesson 8. It's our last lesson in Unit 2. We're looking at solving rational equations and inequalities today. This will be a long lesson. There's 12 examples, so you might want to break it up a little bit. We can say every rational equation can be written as f of x over g of x equals 0, where f and g are polynomial functions. They don't have any common factors. So if that's the case, the zeros of the numerator will be solutions of the equation. And we've seen that when we've been graphing rational functions. In order to be able to solve an equation with fractions, you want to start by finding the least common denominator of all the terms. And then you can clear the fractions from the equations if you multiply both sides of the equation by that least common denominator. One thing you want to look for, though, is the fact that you could introduce extraneous solutions. So whenever you multiply or divide an equation by an expression that contains a variable in it, you just have to be aware of that. And the resulting equation may have solutions that aren't solutions to the original equation. And you just want to double check that solution back into the original equation to make sure you haven't introduced some extraneous solutions. So let's give a couple of these a try. And I'm just repeating myself right there. Okay, in this case, you have three fractions, x divided by 1, 1 divided by x minus 3, and 1 divided by 1. So we can tell by looking at that equation that the domain is restricted at positive 3. We would not be allowed to have positive 3 for a solution. And our least common denominator is going to be x minus 3, since the other two denominators are 1. So what we would want to do is multiply x minus 3 on both sides of the equation. So looking at that, we've got x times x minus 3 and 1 over x minus 3 times x minus 3, and then 1 times x minus 3. So in this first term, we're going to end up with x squared minus 3x. But in the second term, when you use distributive property, we're going to get x minus 3 divided by x minus 3. So that's just going to leave us with a 1. And then on this side, we've got x minus 3. Now we can collect like terms to one side. And that would give us a 3x minus an x, so 4x on the left. And then a 1 plus a 3, that would give us a 4. Factoring that, it looks like we have a perfect square trinomial, since x minus 2 times x minus 2 would give us that trinomial. And then solving for the two factors, x minus 2, multiplicity 2, we're good to go. We know we can plug in 2 back into the equation, and 2 plus 1 divided by negative 1 would make negative 1 for this term. So 2 minus 1 equals 1, and we know that answer checks. So that one was a pretty simple Algebra 2 review type thing. In this case, a little bit more complicated here. You can see that the domain is restricted. We are not allowed to have division by 0, so I can't have 0. And in the second term, we can't have a 1. So those would be extraneous if we got those solutions. And this is just a product of these two factors together. So same restrictions hold. And then our least common denominator would be x times x minus 1, or x squared minus x. So when you think about the entire equation here, approach this one a little bit differently, just for brains that think along these lines. I'm multiplying each term times x squared minus x. So if you're thinking about x squared minus x on each one of these terms, and like I said, I'm just doing it different this way just so you can process through another approach. If you think about this, the x's in the numerator and denominator are going to cancel, and we just need to multiply x minus 1 times x plus 2 in order to clear that fraction, which is going to give us x squared plus x minus 2. In the second term, we're going to cancel or simplify with the x minus 1, so we're multiplying by negative 4 times the x. And then in our third term, this factor in the top and that factor in the bottom are the same, so we end up with just a plus 2 there. While the right side of the equation, anything times 0, still leaves us with 0. So we've got all the terms together. We just need to collect them. And the 2's are gone. And factor. And then the zero product property says anytime two factors are multiplied together and the answer is 0, one of those factors or the other factor must be 0. And you can see we can't have division by 0 from our original statement. That's a domain restriction. So we should be allowed to plug 3 into there and have that work. I'm going to leave that step to you. This one is extraneous. It's a little more complicated. So we're going to look at polynomial inequalities. The remainder of our lesson is going to be about inequalities. Whoop, lost my screen. So polynomial inequalities, we're going to be able to solve inequalities that involve polynomials and rational functions using algebraic and graphic techniques. We want to know if a function is greater than 0. That means the function graph would lie above the x-axis, so the y values would be positive. And if a function is less than 0, the y values would be below the x-axis, and in that case the y values would be negative. So we're on a search for something along those lines. This first one is a cubic polynomial, and our job is to find the real values that cause y to be 0, positive, and negative. And we're going to try this with an algebraic approach using a sign chart, knowing that the function is going to be 0 when the factors are 0. So that's going to happen at negative 3 and positive 4. We also know that at negative 3, the graph is going to cross the x-axis, and at positive 4, with multiplicity 2, it's going to touch the x-axis and turn around. So we could kind of skip up here to the next slide and, whoop, did I not, yeah, where did that go? I don't have that slide. So graphically, hold on a minute, let me find my slide. I guess I didn't make one. Anyway, I'm going to show you on this paper what I'm thinking. Graphically, we know if we have x plus 3 times x minus 4 quantity squared, and that would give us an x times an x squared. We got a cubic function. The end behavior is going to cross and then do something over here. We just don't know what. Is it going to just touch and go back? Or is this section going to dip down below? Can it touch and go back? Is that possible? No. So we know the behavior of the graph is going to look something like that. It's got to touch at 4, cross at negative 3. So just along the lines, we kind of have a feel for what's going on. in this particular situation. I just want to approach it using a sign chart method. So the way the sign chart works is we're going to set up the critical numbers. -3 is a critical number, +4 is a critical number, and I want to test some numbers and see what the sign of the y value is at those test values. So that would look something like this. Let's say we picked -4 to be our test number. If you plug a -4 into this factor, that's going to be a negative number. If we plug a -4 into this factor and square it, that would give us a positive number, which tells me a negative times a positive is going to be a negative y value. In other words, the graph is going to be below the x-axis. In this section on the interval, let's say we tried x equals 0. If you substitute 0 here and 0 here, we've got a positive times a positive. So the graph is going to lie above the x-axis. And then in our last interval, being divided by the critical numbers, let's say we tried 5. Substituting 5 into each factor, we would get a positive times a positive. So our end result would be a positive y value. And now I can go back and answer the question. Our graph is 0 here at these two critical numbers. Those were our zeros. So the location where the function is positive is in between -3 and +4. At 4, it's 0, so we're skipping over 4. And from 4 to infinity, the graph remains positive. So just like we realized in our end behavior model graph, the function's going to be negative or below the x-axis from -infinity to -3. So this approach is called using sign charts. It's really effective, and once you learn how to use them, they become really handy later on in other courses. So this one, we're going to do the same thing, but we've got two inequalities, and what we want to do is isolate all the variables on one side in descending order. And since it's less than or equal to, we'll say it's less than or equal to 0 since we subtracted and moved everything to the left. Now you can factor out an x squared in the first two terms, and you can factor out a -4 in the third and fourth term. And you see we have common factors. X squared minus 4 is x squared is a common factor of x minus 4, and -4 here is also a common factor. Breaking this piece up, the difference of two squares, we have x plus 2, x minus 2, and x minus 4. That way, we know our critical numbers are -2, +2, and +4. So we're going to take these three values, those are our zeros, to a sign chart. -2, +2, +4, and we want to pick out some numbers that we want to test to get the value on the graph, right? And our goal is, where are those y values less than or equal to? So we're looking for that truth statement. And if we tested -3 and 0 and 3 and 5 into that factored form, which was x plus 2, x minus 2, x minus 4. If we tested this number, our value of y would end up being negative, and negative means it's less than, so this segment is true. If you put a 0 in each one of those factors, we get a positive y value, so this section is false. And if we substitute a 3 in here, and here, and here, we got a positive times a negative, so it's negative y value, and this section is true. And then again, substituting 5, we get a positive, so that section is false. And what did we find out? At -2, there's a 0. At +2, there's a 0. And at 4, there's a 0. And they were multiplicity 1. So this was a cubic. And I believe 16 was my y-intercept. So we came up here, came back down at 16, we crossed, and then we crossed that way. So our cubic looks like this, and you can see where the solutions are. So this section up to -3 is true. I'm sorry, not -3, that's -2. And it was less than or equal to, so we want to include that portion. I'll fix my graph here. That should say -2. And then between 2 and 4, that was also a true section. So including 2 and including 4, the graph was also less than or equal to 0. And if we take out the highlighter, you can see what we're talking about here. The highlighter. Yeah, where's the highlighter? I had it. Misbehaving here. Let's try that again. So if we take out the highlighter, you can tell right here and right here, the inequality is less than or equal to 0. So every now and then you need to write that with a number line graph. And again, my highlighter is misbehaving. So we could write that with a number line graph down here under my set builder notation or interval notation. And using the highlighter or using the number line, we know that it works for all the numbers less than or equal to -2, and also for the values between 2 and 4, including the endpoints 2 and 4. So whether you're asked to write in set notation or graph the solution set as a number line, either one are acceptable. In example 5, we want to think about the rational type of expression. So the last one was a polynomial, this one's a rational. We know where the zeros are. The zeros come from our numerator at -3 and at +5. And we know where the function is undefined at zeros in the denominator. Those create vertical asymptotes. So we want to explore that on the next slide and then come back to this. So we've got a break at -3. That was a 0. We had an undefined at a half. That's our vertical asymptote. And we had another 0 at 5. Now I happen to know that there's a slant asymptote since the power in the top was squared and the power in the bottom was linear. So we had x minus 1.5 is our slant asymptote. I'm not going to take care of that work. We know that -3 and +5 are zeros. And we also know if we plugged in 0 into the equation, we would have -15 on the top and -1 on the bottom. So this graph has to cross at 0, 15. It's got to go that way. And this branch of the graph has to hover close by that vertical asymptote and come around here. So using our skills from last class, we graphically can tear this apart and piece the graph together and then look at the graph and know if I tested a number here, such as -4, you change colors here. If I tested -4, I'm going to be below the x-axis because I'm over here. If I tested a number like, let's say, 0, I'm going to be up here at 15, so that's going to be positive. If I tested a number to the right of a half, so maybe we tested something over here, say 1, I'm going to be negative down here. And if we tested 6, we would be positive. So now I know the behavior of the graph. It's below, above, below, above. And we want to go back to that last screen. So we can say the function is positive from -3 to a half. And then it's positive again from 5 to infinity. But we're not including these endpoints because it doesn't say equal to 0. It's just asking positive. The negative regions would be everywhere else between -infinity and -3. And then also on the segment between a half and 5. Okay? Using sign charts, using our skills from graphing from this unit, piecing all of those together and actually using them to solve some problems. So we can continue on that journey solving rational inequalities. Remember what we're looking for. There's 4 steps here. And this is what I just showed you in that last example. This means I'm above the x-axis, or the y's are positive. This includes the zeros. F of x is less than 0 means that you're below the x-axis or negative, and this one again includes the zeros. So you just have to be careful to read what you're looking for as you go through these exercises. After you figure that out, you want to find the values that make the expression 0 or where you have a vertical asymptote. Those we're calling our critical numbers. And we're going to use those critical numbers to separate the number line in intervals. Then we're going to test some values to figure out the sign of the expression. And if it's positive, that's above. If it's negative, that's below. And if it's equal to, we want to include those values in our solution set. So that's our procedure. And we've got 3 or 4 of those to do. And they're a variety of different types. So you can see x minus 3, that's a 0. And x is -2, that's a vertical asymptote. So we have don't exist here. And at 3, we have a 0. And we're looking for test numbers. We want to test numbers, and we want to find the value. And what are we looking for? We want y value. We want our value to be a positive number. Okay? So if we test -3 and 0 and 4 in each one of these little intervals, we're going to end up with a positive number here because we'll have a negative divided by a negative. If you substitute a 0 there, we're going to have a negative in the top and a positive in the bottom. And if you substitute a 4 into our expression, we're going to have a positive divided by a positive. And we want to know where the solution is above the x-axis or where the y values are positive. So that would happen in this section. It would be true. So our solution would be from -infinity to -2. The middle part of the interval is false, and the end of the interval is true. So we've got 2 sections where the solution is true. Pretty easy, right? In example 7, can you write the inequality in standard form? So this one's a little more complicated. We have to subtract 5, and we also have to get a common denominator. So our common denominator would be x plus 2. after we subtract 5, we've got to have x plus 2 in the bottom to be able to subtract them. So we need an x plus 2 least common denominator, and subtracting 5 leaves 0 over here. So cleaning all of this up, we'd have x minus 2 minus 5x, so that looks like minus 4x, and then negative 10 minus 2 is negative 12 over that common denominator. So we're taking our critical numbers from this expression, and if you factored out the negative 4, then our two critical numbers are going to be negative 3 from the numerator and negative 2 from the denominator. This one's a vertical asymptote. This one is a 0. And we want to test some numbers. We could test negative 4. This one we could test negative 2.5. And I like using 0. Okay, so again, I'm thinking about plugging a 4 into here. Or if you plug a negative 4 into here, you've got to consider, is it above 5 or below 5? So I'm plugging my 4 into here, and I've got a negative 4 times a negative 1. So I've got a positive in the numerator and a negative in the denominator. So this section is false because it's below the axis and we want above the axis. Plugging in a negative 2.5, we're going to get a negative in the numerator and a negative in the denominator. So this is a true section. And if you substitute 0 into our expression, we're going to get a negative in the top and a positive in the bottom. This is my only true section. So our solution set, remember we're wanting y's greater than or equal to 0, so it can include the zeros. This one's a 0. This one's a vertical asymptote. So we can include negative 3, but we cannot include an infinite discontinuity. This is going to be our solution. So that one's a little more complicated. And this one even more. This time they want us to give the solution in set notation and give a graph for it. So in the same way, I want to move this term to the left and multiply by my least common denominator. So this term, the 3 needs an x plus 4, and the 1 needs a 2 minus x. You follow along with that? So we've got 3 times x plus 4 divided by 2 minus x times x plus 4. And keeping all that together, if I subtract 1 and multiply that term by 2 minus x, then we have a common denominator, and our numerator looks like 3x plus 12 minus 2 plus x over that common denominator. And collecting like terms in the top, we have 4x plus 10 over that common denominator. And then I want to go back, if you'll let me do this. Let's see, 4 has 2 that's common and a 5 that's common. So we could put 2 times the quantity 2x plus 5 in our numerator. Let's do that. 2 times the quantity 2x plus 5. And we want this expression to be less than or equal to 0. Okay, so that was a lot of algebra. You with me? Hopefully. Our critical numbers, we have one vertical asymptote at 2, we have another one at -4, and we have a 0 at -2.5. So on my number line, I have a vertical asymptote at -4, a 0 at -2.5, and another vertical asymptote at 2. And we're going to test, I'm going to test -5 and -3 in this section, 0 in this section, and testing 3 in this section. And here's what happens with my signs. Remember, I'm plugging this number into this expression over here and comparing whether it's less than or equal to 0. So I've got a negative in the top and a positive times a negative in the bottom. So this section is positive. That means this is a false section because it's above the axis. If we plug a -3 into here, we've got a negative and 2 plus 3, is that a positive? And a positive. So this section is a, did I do that right? I've got -6 plus 5. So 2 times -1, that's a negative. And 2 plus 3 is a positive. And 3, yeah, so this is a negative number. Oh yeah, so this is a true section. It's having a little brain freeze there for a minute. If we plug in a 0 here, we got a positive and a positive and a positive. So this is a false section. And then plugging a 3, we've got a positive divided by a negative times a positive. So this is a negative, and this would be a true section. So true, we're true. Our solution is true from -4 to -2.5, and we want it less than or equal to, but again, -4 is a vertical asymptote, so we can't include -4, but we can include the 0. And then 2 is a vertical asymptote, we can't include that. And we're on to infinity. So if we're graphing this on a number line, -4, -2.5, +2, we would have an open circle and a closed circle shaded in between. And at 2 would be an open circle and shaded to infinity. So that one was a little more complicated. Here's one that has absolute value and it's rational. So we know that we can't have -1 and we can't have 4. And I'm testing values like -2, 0, and 5, substituting in here, and we get a negative y value in this interval. We get a positive y value in this interval, and a positive y value there. So this section is false, this section is true, and this section is true, and it's equal to. But what's happening? This is a vertical asymptote, right? We can't do that. And this is a 0. So our solution would be including -1 up to 4, that's a vertical asymptote, on the other side of the vertical asymptote to infinity. And if you had to draw the graph, because that's what they wanted us to do, between -1 and 4, we would close up -1, but skip over 4 and shade all the way to infinity. Now with my calculator, I graphed that so you could take a look at the function itself. Let's see how that looks. Okay, so we were above the x-axis from -1, and then on the other side of the vertical break, all the way to infinity. Interesting. Here's one for you to try. You might want to turn the video off and come back to check. So my critical numbers are at +2 and -1. And another interesting fact is this: at -1, we can't put a -1 here, or -2 here, because -2 would not be a solution for this factor. So all of this section over here is undefined on the graph. And 2 is the other critical number. So these are zeros, but nothing can be out here. And we could say this is not existent. In this section, if you substituted 0 in there, we would have a negative answer. And if you substituted a 3 into our inequality, we'd have a positive answer. And we wanted y's to be negative, so this is the segment that's true. The solution would be -1 to 2, including those because our inequality said less than or equal to 0. And there's a picture of that graph, so you can have a look at that. Okay, 2 more and then we'll be done. This is, like I said, this is a long lesson. So in this case, we're going to move the 2 over to the left-hand side, giving everything the same denominator. We need a common denominator, 1 minus x. So when you subtract 2, you need to multiply that by a 1 minus x in order to be able to move it to the other side. So we've got x squared minus 3x minus 10 minus 2 plus 2x, and I'm not paying attention to what I'm doing there. That should be a 0. We're all over the common denominator 1 minus x. Getting common terms, collecting like terms. That gives us a polynomial that will definitely factor. And the factors will be x plus 3 times x minus 4 divided by 1 minus x. So we're getting our critical numbers from this expression here. Going back up to our number line. So we have a critical number at -3. We have a critical number at +1, which is a vertical asymptote. This was a 0. And then our other critical number is at 4. So we could test -4, 0, 2, and 5. And this one would end up being a positive. This one would end up being a negative. This one is a positive. And this one is a negative. So the true statements are positives. These two segments, intervals, are true. So our solution would be from -infinity to -3 and from 1 to 4, but I'm not counting 1 since that's a vertical break in the graph. In the graph, we could do the same thing as before. We would want to color in at 4. It includes 4, an open circle at 1, and then closed in at -3 and shade to infinity. So those can be a little challenging, but like I said, it's a great skill to have. Then we got 2 word problems here. In this case, we want to throw a ball vertically, and we want the ball to be above the tower. It's being thrown off a tower that's 190 feet tall. So that sounds like I'm taking negative 16t squared plus 96t plus 190, and I want the path of that ball to be above the tower, and the tower is 190 feet tall. So if you subtract 190 from both sides, we end up with negative 16t squared plus 96t has got to be greater than 0. And this is just a basic Algebra 2 question. So t could be bigger than 0, or actually in this case, it's going to be less than 6, because if you know the path of vertical motion, if we start up here at 190 and you throw a ball and it goes up, then the ball crosses at 6 and at 0. So it's this section in between 0 and 6 where the ball is above the tower. So we could say the ball is above 190 feet on 0 to 6 seconds. And then after that, it's on its way to the ground. Okay, last one. Florida Paper Products has a contract to make a box with the volume of no more than 200 cubic inches. So we know volume is length times width times height. And this cardboard box, this cardboard is 15 inches this way, but we're going to cut a square out of both sides. That's 15 minus 2x. And it's 18 inches this way. And again, we're going to cut a square out of this side and that side. So this is 18 minus 2x. So what do we know? The volume is going to be 18 minus 2x times 15 minus 2x times the height is x, because when you fold these up, that's going to make the box. And that has to be no more than, so it can be exactly, but it can't be any more than 200 cubic inches. When you FOIL this out, you end up with 4x cubed minus 66x squared plus 270x. And when you subtract 200, we're looking for where it's less than 0, right? Less than or equal to. And using my calculator, I find that happened here at 0.95 inches, at 5 inches, and at 10.5 inches. But we got a problem with this one. When you go back and look at the equation, this short side of the cardboard, if you folded it 10.5 inches, you wouldn't have anything left to make a box with. Does that make sense? So we would have to say, Houston, we got a problem here, because the short side of the cardboard, I'm going to call it the stock, causes a domain restriction. And that restriction would be half of that. So we can't have no more, the domain has to be less than 7.5 inches to cut out of the square, because if you cut 7.5 inches out, you're cutting that cardboard in half. There's nothing left except 2 halves that are 7.5 inches. Does that make sense? So we could finish this up by saying out of this cardboard here, based on that graphic, the solution would be to cut squares that are somewhere between 9.5 inches, right? From 0 to 9.5 inches. I'm sorry, not 9.5, 0.95 of an inch. Cut a square between 0 and 0.95 of an inch. or you can cut squares that are between 5 and 7.5 inches. Let me go up here and fix this. This looks, cut squares that range from 0 to 0.95. It could be exactly 0.95, or cut squares between 5 and 7.5, because you see this line is y equals 200, and that volume is below 200 in here, and it's below 200 here, right? But we can't go past 7.5, because then you have negative area. So we can stop right there. That's the end of chapter 2. Gonna be seeing a test pretty soon. Bye.